All right, so welcome back. This will be our second module in the course. So we're going to move from the basics of what is science, what is physics, into the first chunk of physics, which would be kinematics. And that's just a fancy way to say the study of how things move. So essentially just taking math and applying it to what we see when objects are thrown into the air, things like that. So in this module, we're going to essentially talk about the three main features of kinematics: speed, velocity, acceleration. And then we're going to move into free fall. That'll be a whole lecture in and of itself. And then we'll talk about projectile motion. That'll be the third portion of this module. So in regards to speed, Galileo is actually credited with being the first to measure speed by considering the distance covered and the time it takes to cover that distance. Okay, so we've got a distance, we've got a time it takes to do that. Galileo defined speed as just the ratio of those two things, distance over time. And if you think about it, that's where our definition of speed, it still comes from that. Distance per time, in our case, miles per hour. If you're in Australia, kilometers per hour. So this will be the per. So this is a rate, which is just how something changes with respect to something else. Okay, so the distance can change, or there's a specific value of distance that correlates with a specific value of time. And we can have lots of different rates. Just as an example, here's something that a rate that I used to use when I taught statistics and we were doing Poisson distributions, which involves rates. So suppose a beginner baker accidentally, on average, gets 3 pieces of eggshell in his batter. Okay, so this rate is 3 pieces per cake, or 3 pieces of eggshell. Okay, so this is the eggshell. Okay, and that'll be on average 3 of those in each cake. And of course, that's to be read per. Now, if the baker makes 3 cakes, one might expect there to be 9 pieces of eggshell between the 3 of them. Okay, that makes sense if we expect 3 per 1 cake, and there's 3 cakes. Well, then we can multiply the number of things by the rate of the thing happening. And that tells us, in this case, how many pieces of eggshell we would expect. So let's actually look at the units here. Okay, so if you made 3 cakes, okay, and then we expect 3 pieces per cake, or 3 pieces of eggshell per cake, but we can multiply by the rate. Okay, and then that's just 3 cakes times 3 pieces per cake equals 9 pieces. Notice that the units cancel out. Okay, I'm going to switch. Units work like fractions, so we have cakes here in the numerator, cakes here in the denominator. Keep in mind that we can rewrite this as cakes over 1. Remember, when you're going to multiply fractions, you can write just a number as a fraction, so like 3 is the same thing as 3 over 1. We're going to do the same thing with units here. So really this is just cakes over 1. When you multiply straight across, we have a cakes in the numerator, cakes in the denominator that cancel out. And we're left with pieces. Okay, so beginning baker, 3 cakes, 9 pieces of eggshell amongst the 3. Now we can use, going back to velocities, we can use really any units we want to. Any combination of a distance and a time, we can use that to represent speed. So for cars, where you're traveling long distances over hours, it makes sense to use something like miles per hour or kilometers per hour. And we can represent those as fractions, just the rates, miles per hour, kilometers per hour. But for shorter distances, like maybe if you're running somewhere or walking somewhere even, you can use feet per second or meters per second. Same thing applies, it's just the ratio. Uh, we could even represent our walking speed in terms of miles per hour if we wanted to. It would just sort of be an awkward number because it'd be really small. So, some interesting history as far as the slow move to start standardizing all these measurements from way back in the day. Um, Used to in European countries and other places, like every little town would almost have its own unit of measure. So when you tried to work on things collaboratively among lots of towns, trying to maybe, build a bridge between the two, it got really confusing. Um, so this dude Akbar ruled over much of India between the 1500s and 1600s. Um, he actually worked to standardize many units of measurement. And one example of this was he used the barley corn as a unit of weight. So that's just this little piece here that comes off barley, and about three of those together equals an inch. So he started using these as a standard of weight, and then later on, the barley corn actually became more used as a unit of distance. So I think there's actually some European countries that still use this to measure the width of shoes. I'm not sure which country it is, but I think it's out there. Uh, I'll also leave a note here, not just distance like between towns, because that would be insane measuring with barley corns, but also just lengths in general. Um, so in addition to something weird like the barley corn, um, Gilbert Newton Lewis actually defined a time length called a jiffy. So I'm sure you've heard, someone will be ready in a jiffy or the food will be ready in a jiffy. That's actually a defined unit of measurement. Um, so Lewis here, he defined it as the time required for light to travel 1 centimeter in a vacuum. That's in the 1800s. But more recently, and I think more in computer science, the jiffy has been defined as just 1/100th of a second, so 0.01 seconds. And I think, but I'm not certain, that this is for computer science applications. I'll put a question mark since I'm not sure. So the cool thing is, this means that we could measure speed or report speeds as barley corns per jiffy if we wanted to. I mean, that'd be an insane way to report your speed, but you can do it. Back when I was an undergrad, we would sit around and come up with really stupid units of measure for like speed and other rates. Another one would be like your speed could be measured in like furlongs per fortnight or something. So all of these are valid. It's just depending on what you're looking at, not all of these are useful. Depends on if your audience knows what you're talking about. It depends on if this number is going to be obnoxiously large or small. You need to pick what units are going to be most appropriate. But when we measure speed, we can actually measure this in two different ways. We have an instantaneous speed, which is whatever this particle or object is doing at any instant in time. If we know the speed, then that's the instantaneous speed. So you can think about this as like a speedometer in your car that tells you precisely how fast you're going at any given moment. The other way we can talk about speed is an average speed. Okay, so this represents an overall rate given a distance traveled over time. Okay, so since the average speed is the total distance traveled divided by the total time taken, this is important. It doesn't indicate the different speeds and variations that take place during the segments of the trip. Okay, so here's the definition of average speed. You can see, if you go from one side of North Carolina to the other, it takes like what, 6.5 hours. So you take that distance, divide it by the total time, that gives you your average speed, but it doesn't tell you, like, it doesn't reflect that you've stopped at traffic lights, or you were driving on the interstate going 80 miles per hour, or you're driving down a gravel road at some point at 2 miles per hour. So this is just one big bulk measurement for the entire trip. All right, so let's take a look at a very simple example. So if we wanted to know what is the average speed of a cheetah that sprints 100 meters in 4 seconds, okay? So we have our distance, and we have a time. So we have both pieces we need to do this calculation. So we just simply plug in the distance traveled over the total time taken, and its average speed is 25 meters per second. So let's look at something a little more complicated. So if a car moves with an average speed of 60 kilometers per hour, okay, so now we're actually given a speed. We don't have a distance or time. We have a velocity or a speed. Okay. If we know the speed, how far will it travel after 4 hours? So we do have a time. Now we need to figure out the distance. Well, since the average speed and time intervals are known, we have those, we can actually do some simple algebra and rearrange this equation and solve for this unknown distance. Okay, so starting with average speed equals total distance divided by total time, what we can do is we can multiply this total time taken over here. Just like in algebra, we could even write like A equals B over C. Well, we can multiply both sides by C. I'll write it this way, AC equals B C. Right, it's an equation. Whatever we do on one side, we do to the other. Okay, so if we multiply both sides by C, and then we're going to bring in that rule again, where if it's just C, we can write it as C over 1. Okay, so we have our imaginary C over 1. Those C's cancel, and we're actually just left with CA equals B. Okay, well, we're going to do the same thing, except we're going to do it with words and not just symbols. So if we multiply this over, we're going to have average speed times the total time taken, and that's just going to equal the total distance traveled. Okay, well, let's plug in these numbers. We know the average speed, we know the total time taken. So just a simple multiplication. Notice that the units cancel, right? Hours cancel, and we are left with 240 kilometers. Okay, so this, I just want to reiterate that you can think about these units as fractions. Here in this case, our hours cancel, leaving us with just kilometers on top. That's the only thing that survives and gives us a final unit of kilometers. Okay, so that was speed, right? How fast something's going. Let's talk about velocity, because a lot of people in everyday life will use these the same. Speed, velocity is how fast you're going, but there's one difference with velocity. So while the speed of an object provides information about its change in distance over time, velocity provides the same information, okay? So information about its speed, but it has extra speed plus direction. Okay, once you combine these two things, you now have a velocity and not just a speed. So a quantity that requires only magnitude for a description. So this is only magnitude, so basically how much So speed 12 miles per hour or something like that. Another example of a scalar quantity would be temperature. Temperature doesn't have a direction. You don't say it's 60 degrees Fahrenheit to the left. That doesn't make sense. So speed, which just has a number, a temperature, which just has a number. These are scalar quantities. And of course, just that value, a big value indicates a fast moving object when it comes to speed. A small value indicates a slow moving object. This does not provide direction. I could say, oh, I'm driving at 2 miles per hour, but I could literally be doing that in reverse. I could be doing that going forward. I've not given you enough information. Now, if we have a quantity that specifies both a magnitude, so how much it is, and direction, so I'm gonna write that here. How much? Okay, now if we have both, that is a vector quantity. So just saying something like a car's velocity is 60 miles per hour north, that's enough to convert its speed to a velocity. Okay, so you have the magnitude and you have the direction. So just smashing those two things together gives you a velocity. Velocity you can think of as a directed speed. So something with a constant speed doesn't speed up or slow down. Okay, so this is the scalar version. But now since a velocity has two pieces, a magnitude and a direction, we have to extend this a little bit. So something with a constant velocity doesn't speed up, slow down, or change directions. So we have this other piece here when we're talking about velocities. So essentially a constant velocity means the same speed in a straight line, same direction forever. That's a constant velocity. If the speed changes or the direction changes, then the velocity changes. Okay, so you can think about this car. Even if the car's speedometer says the same thing the whole time it's driving, it's still accelerating because the direction is changing. Now, that does mean this velocity is changing, is turning, but I said acceleration, so that's going to bring us into our next point. An acceleration is actually the measurement of how this velocity changes. And this applies even to like this car where we have this constant change in velocity, which is direction and not necessarily a speed. So let's talk about acceleration. So basically the whole idea here is acceleration is how quickly and in what direction velocity changes. Okay, that's our definition of acceleration. And you'll notice this looks similar to what we've been using. It's also a rate, but it's a little more complicated rate because we have a change in something. You know, it's not like a change in distance like velocity, but it is a change in velocity over some time interval. So the key idea here is change, and the units of acceleration are a little weird. Okay, so the definition of velocity involved a change in a distance per time. Okay, so this is a velocity, meters per second, that provides us a rate. Now we have to think about acceleration carefully. Acceleration is the time rate of change in velocity, okay? So acceleration is a change in rate, but it's the change of a change of rate. It's the rate of a rate. I know it's very Inception-y. So I guess the best way to describe this would be to just look at the units. So let's go through the units here. If we start with this original definition up here on the top line, we have acceleration equals change in velocity divided by some time interval. Well, generally when you talk about a change in velocity, you do the final velocity minus the initial velocity. Same thing if you talk about a time interval, you do the final time minus the initial time. Okay, now if we just think about the units, we know for velocities, both final and initial, these are velocities, they're going to have units of meters per second. Okay, now it's just like saying if I have 7 apples and I take away 5 apples, I have 2 apples. So those units are going to track, right? So if I have some ending velocity minus some starting velocity, I'm still going to be left over with a velocity. So that's what's going on in the numerator. Same thing in the denominator. I have some time minus another time. So I'm still going to be left with a time. Okay, so that's going to be down here in the denominator. Now what's really weird is we have, I'm going to try and get fancy, we'll see what happens. So what's really strange is we have this seconds in the denominator and this second in the denominator. So if y'all remember from way back in high school algebra, maybe even middle school, do you remember how to divide two fractions? Because we could rewrite this as meters per second over seconds over 1. Remember, any sort of just number we can write as that number over 1. So when you divide fractions, you flip the bottom and multiply. So instead of s over 1, we have 1 over s. So if we multiply straight across, we're going to get meter over second times second. And just like in algebra, we can just write that as second squared. So that's what's going on here. This is how we end up with acceleration, having the units of meters per second squared. And what this is saying is essentially every second that goes by, your velocity, meters per second, changes by this amount. So this is like saying our velocity changes by 2 meters per second every second. Okay? And then the last thing to note here is that in terms of acceleration, accelerations can be positive or negative, so they can increase or decrease. And usually if you're moving and then you start slowing down, that's going to be called a deceleration. So let's look at an example of acceleration here. So in 2.5 seconds, a car increases its speed from 60 kilometers per hour to 65 kilometers per hour. Okay, so you can see just from the text that there is a +5 change in velocity. Now, a bicycle, at the same time, in this 2.5 seconds, a bicycle goes from rest, so no speed, to 5 kilometers per hour. So which undergoes the greater acceleration? And you can see just from reading the text here, this is also a +5 kilometers per hour. Well, let's do the calculation for the car first. So we have our change in velocity. This is going to be our final value minus our initial value. Okay, so for the car, this final speed it landed on is 65 kilometers per hour. Its initial speed was 60 kilometers per hour. Okay, well that difference is 5 kilometers per hour divided by 2.5 seconds. That actually gives us 2 kilometers per hour per second. So really what this is saying, I'm going to try to write it as nice as I can, is that every second the car speeds up by 2 kilometers per hour. Okay, now if we do the same thing for the bicycle, Well, we have the final velocity, which is 5, and it started at 0. Okay, and we divide by the 2.5 second time interval. So we weren't given an initial time and a final time, but we know the interval. We know whatever those times are, when we subtract them, it's going to be 2.5 seconds. And what's interesting is we get the same exact acceleration. So it doesn't matter that the car is traveling fast already and the bicycle's starting from rest. What your initial speed is doesn't matter. It's how that speed changes. It's how that velocity changes. So they actually both have the same acceleration, even though they're both traveling at very different rates. Okay, this is sort of just an aside. So note that in the previous example, only the magnitudes of the velocities were changing. That means they weren't driving in different directions. They were both driving in straight line motion. So when that happens, we don't have to say velocity. If everything is happening in straight line motion, we can actually just revert back and call it speed, because we know the directions. We know the direction's not changing. So in these situations, it's okay to use speed and velocity interchangeably, but if there's a change in direction, you have to stick with velocity. So just a couple of other notes. We accelerate whenever we move in a curved path, even if we are moving at a constant speed. So remember the car driving in the circle? Even if its speedometer never changed what it was showing, it's still changing its velocity because its direction is changing. So yeah. And then because that velocity is changing, that's going to cause an acceleration. Something important to note here, zero acceleration that does not mean the object is sitting still. It could still be moving. It could be just the hauling, but if it's doing that at the same speed the whole time, in the same direction, the acceleration is 0. Something else to note is that an acceleration can actually act in the opposite direction of your velocity. So that would be a deceleration. You can see over here in this image, we've got some car accelerating because we've got a label of acceleration here. So we've got some car speeding up toward the cliff. It's pointing in the same direction as the velocity. So when they're pointing in the same direction, you're going to get an acceleration. Now, when this car realizes that there is a cliff, you'll see that it tries to slow down. It's still heading toward the cliff, but now its acceleration is opposite the velocity. So here's the decel. So this is a deceleration. This is the acceleration. Okay, and then even though it leaves the cliff here, what the thing causing its acceleration to change here is the fact that its velocity is changing direction. Okay, so this change in direction from going straight across to pointed downward, that's causing an acceleration as well. Well, I take that back. It's not causing the acceleration, but this gravity pulling it down is causing this acceleration. But mathematically speaking, you can calculate it by the change in velocity. So since the velocity starts pointing down, the amount that it's pointing down is actually where your acceleration value comes from. I want to make sure I get that nuance in there. So Galileo developed the concept of acceleration. He was the one that did all these experiments, like we talked about on the first slide, to actually define speed and start developing kinematics. So he developed the concept of acceleration through experiments with inclined planes. And this is actually pretty clever because it's hard to measure something if you just drop it and it hit the ground and try to time it. He didn't have accurate timing devices at all. He actually, I think, used his pulse as a clock, and that depending on how excited he was about what he was doing, that could change his results dramatically. So he had a clever idea to actually put things on inclined planes, because that slows their motion down. You can imagine if you have a horizontal surface, put a ball on it, and just barely tip it, that ball is going to accelerate, and it's going to have all the aspects of acceleration, but it's going to do it slowly, and then you can time it. So he did find that a ball rolling down an inclined plane picks up the same amount of speed each second. Okay? So this indicated constant acceleration. So that means you're getting the same amount of speed each second. So if this is the first second, you get a speed boost. Second, so if this is T1, T2, you get plus the same amount of speed boost every time. So since the velocity is continuously changing each second, because you keep getting that boost from the ramp, the instantaneous velocity may be calculated by rearranging the acceleration equation. So that is a good point, and something we'd want to calculate is, well, if our velocity is changing, if it starts from rest at 0, and then it's just really hauling down here at the end of the ramp, how can we calculate the velocity at the bottom or a velocity at any of these other points along the way? So if we look at this figure over here, you'll notice that the A's here, they keep getting larger because the ramp keeps getting steeper. The idea is essentially the steeper the slope, the greater the acceleration. And that's pretty much common sense. I'm sure you all have rolled a ball down an inclined plane before. Something to note here is that the position of the ball is shown at each second. So this is like T1, well, let's call it T0. This is where it starts from rest. Then after 1 second, this is T1, T2, so on and so forth. But what do you notice? This is something worth noting here. After each second, the distance keeps getting larger. And instead of like the velocity being added to by the same amount, the distance after each second keeps getting more and more added to it. So if we like increase this ramp by a lot, look at the difference here in this T0 and T1. So we have these two positions. That distance between these two is further apart than in our original example. That's because the acceleration is increasing. So the more and more we make this incline vertical, the more distance we're going to have in between these snapshots. And even when compared to itself, these distances are going to get progressively larger and larger. So you can see if we wanted to even compare, like on a smaller incline plane, after what is this, T1, 2, 3, no, T0, 1, 2, 3. So between like T4, T5 here, this distance is not as large as this distance. Same time interval, just a steeper incline. And then of course, if we tilt this all the way up towards vertical, this is when our acceleration is a maximum. We can't make it any larger than this. And this is just acceleration due to Earth's gravity. And we generally just call that G. It's a nice shorthand notation. So getting back here to this whole calculating the instantaneous velocity, because clearly, whatever the velocity is here is not the same as what the velocity is later on, because it's increasing, it's going down a ramp. So let's take this original definition, acceleration equals change in velocity over time interval, and let's rearrange this as well. So all we're going to do, same thing as last time, we're just going to multiply the time interval part over, and that's just going to give us acceleration times time equals change in velocity. Okay, so we're going to write it essentially in a shorthand notation. And you'll notice I've used some deltas here. So these are deltas. They're Greek letter delta. And all a delta means, so like delta V, is just the final value minus the initial value. In that case, a delta T would be the final time minus the initial time of the time interval. That's all the delta is. This is about as compact as you can make these equations. So essentially, the instantaneous speed at any time is equal to acceleration times time. Essentially how long that acceleration has been in effect. Okay? So Galileo found that acceleration was constant for each incline. So this value of A was the same for each incline. Okay, and as he increased that angle, so this angle here, ooh, it's hard to see. So as that angle increased, that value of A would increase, but it wouldn't change throughout the incline. So whatever value of acceleration you have here, same value of acceleration down there. So regardless of the weight or size of the object, Galileo discovered that if you could ignore air resistance, all objects pretty much fall with the same constant acceleration. And what we're talking about is that free fall gravitation from the Earth's mass. If you drop things and you could ignore air resistance, everything's going to fall with that same acceleration of g. So I'm going to stop here, and that hit our three main things: speed, velocity, acceleration, and like distance. So yeah, we'll pick this up talking about free fall in the next lecture, and we'll actually get into this value of g and what it means and how it works.